Hello and welcome. My name is Dr. Mark Taylor. This is the Delaware Tech Physics 111 Lesson 7, Part 1. Lesson 7 is the fourth lesson of Unit 2 on forces and energy. In Lesson 6, we discussed work, which is a method of transferring energy, but in this lesson, Lesson 7, we will discuss energy itself, its various forms, how they're converted from one form to another, and how to calculate many of these forms. So we're going to talk about energy. We're going to talk about its many forms. We're going to discuss the two main categories that energy is found in: mechanical forms of energy and non-mechanical forms of energy. And then I'll show you a chart that organizes the various forms within the mechanical and within the non-mechanical so you can keep track of them. We'll talk about the concept of conservation of energy, and then we'll talk about some of the specific forms of energy. Among the mechanical forms of energy, there are kinetic energy and potential energy, and there are multiple forms of potential energy. We'll talk about two of them: gravitational potential energy and elastic potential energy. And when you add up all the kinetic with all the potential, you get what's called mechanical energy. And we'll talk about how to calculate kinetic energy and the gravitational potential energy. Any form of energy that's not mechanical is considered non-mechanical energy, and we'll list those. You don't need to know how to calculate them, but you should know what they include. Then we're going to talk about something called the LOL, energy flow diagrams. And LOL does not stand for laugh out loud. In fact, it doesn't stand for anything. The LOL refers to the shapes of the individual diagrams within the energy flow diagram. So the first diagram looks like an L, the second one looks like an O, the third one looks like an L. And finally, we'll discuss the PHY energy skate park simulation. PHY stands for Physics Education Technology. This is a series of physics simulations created by the University of Colorado. What is energy? Well, one fairly straightforward definition of energy is it's the capacity to do work or produce change. What kind of change? Well, any kind of change in matter, where you're moving the matter or you're converting the matter from one form of matter to another, and that could be a lot of different things. So energy is both a thing and a process that involves moving matter or changing matter. And it helps us describe the interaction between energy and matter. Energy is frequently only observed when it's actually being transferred from one object to another or transformed from one form of energy into another. So this would include things like when work is done, when you're moving something using a force, or heat is transferred. So that's the part of the internal energy of an object is being transferred from one object to another, one system to another, or when you have chemical reactions. Energy itself, just like we learned about work, it's a method for transferring energy. Energy is a scalar quantity. It does not have a direction, though it can be transferred to and from one place or another, but we don't represent it with arrows because it's not a vector. And the unit of all forms of energy, just like work, which is one form of transfer of energy, the unit of all forms of energy is the joule, and the joule is equivalent to a Newton times a meter, or a Newton meter. Well, it turns out there are quite a few forms of energy, and we'll discuss a handful of these that you'll be responsible for, but there are many other forms. So the main forms I want you to be aware of are kinetic energy and potential energy. Kinetic energy is essentially the energy due to an object being in motion, so it having a speed. And potential energy can be thought of as the energy of an object because it's in an unusual position that makes it somewhat unstable. And we'll talk about these in detail when we get to the section on potential energy. There are multiple types of potential energy. The two that you'll be responsible for at least understanding are gravitational potential energy. This is the potential energy due to being high above the Earth. And that high above the Earth could be 1 meter above the ground, or 50 meters above the ground, or 200 meters above the ground. As you get higher, you have more potential energy because you have the potential to fall further and gain speed as you're falling. Elastic potential energy is the potential energy when you have a spring that has been either compressed or stretched so that the second you let it go, it will move immediately. So these are both forms of energy where there's no movement initially, but if you let them go, they will do something that will create movement and therefore create kinetic energy. So we're going to learn about kinetic energy and how to calculate it, and potential energy, and we'll learn how to calculate the gravitational form of that. These two major categories of energy make up what we call the mechanical energy, and everything else is called non-mechanical energy. There are many forms of that. The three that you should be aware of are internal energy, sound energy, and deformation energy. Internal energy is the energy within the molecules and the atoms that the matter is made of, and this includes the movement of the molecules and atoms, that microscopic or submicroscopic movement of particles, as well as the various energies of the bonds that are involved in making up that matter. Sound energy is more technically called acoustic energy, and this is the energy associated with a sound wave, and we'll talk more about that in Unit 3. And then deformation energy, this is essentially when something gets bent or broken when it's been hit or some strain has been put on it. It's technically called the elastic strain energy, but if somebody asks you what are the non-mechanical energies, you would just say internal energy, sound, and deformation, and that would be good enough. But there are many, many other types of energy, and most of these fall under the category of non-mechanical energy, including electromagnetic energy, which we touch on in Unit 4. This is related to the energy of all forms of light, not just the light we can see, but all forms of light. Chemical energy, which is part of the internal energy I mentioned. So that's the potential energy stored in high energy bonds or less stable chemical compounds. And then nuclear binding energy, this is the energy involved in holding a nucleus of an atom together. And there are quite a few others, but you're not responsible for any of these in this particular unit. So let's organize these energies in categories. I mentioned the two big categories are mechanical energy and non-mechanical energy. And the mechanical energy, as I mentioned, is the sum of the kinetic energy and all the different forms of potential energy, at least the large scale ones, the ones you can see. We're not talking about the tiny ones involved in atoms and molecules. We're talking about the whole object. So in this course, we'll define mechanical energy in a certain way, but you'll find that it's defined in a variety of different ways. So we'll think of it as the type of energy or energies based on just a handful of large scale variables. What do I mean by large scale variables? Things you can look at and measure very easily, like the speed of an object, or its position, how high above the ground it is, or how much it's been stretched or compressed, etc. And the mechanical energy is energy that can easily be transferred to cause some kind of visible, obvious movement or change in the matter. And that energy can be readily used to perform work, as opposed to non-mechanical energy, which is much harder to harness to actually do work with. So again, mechanical energy is just the sum of the kinetic energy plus all the different potential energies. Non-mechanical energy is everything else. It's the form of energy that's usually due to many, many tiny motions. When I say tiny motions, I mean the motions of atoms and molecules and even subatomic particles inside of matter and their unusual positions. Energy from non-mechanical energy is hard to be used to move matter or change matter at a macroscopic scale, and therefore it's not easily used to perform usable work. We will count non-mechanical energy, as I mentioned before, as the sum of internal energy. This is the internal movement of thermal energy, as well as bonds of a wide variety of bonds, as well as sound energy, that is acoustic energy, and deformation energy. And it's the sum of those things. But remember, the total energy is just the sum of the mechanical and the non-mechanical. So below here is just a little tree diagram to show you the organization. You have the total energy. It falls in two categories, mechanical and non-mechanical. The mechanical is made of kinetic and potential, and there are various kinds of potential. And the non-mechanical is everything else. For your purposes, it's internal energy, sound energy, and deformation energy. But there are other things that we measure in the same units as energy, like work and heat. But these are methods of converting energy or transferring energy from one place to another. That's a separate thing. Now, while it's important to understand that these various forms of energy can be converted into one another, there is a conservation of energy. That means that energy is never lost. It means that if you looked at the total of all the different energies in the beginning of some interaction and all the energies at the end of the interaction, and you added them up, the sum of the energies in the beginning will exactly equal the sum of the energies in the end. The energy is conserved. It may be converted into other forms, but it will never be created. It will never be destroyed. It can only be converted between forms. And sometimes that conversion is easy to do, and sometimes that's a little difficult to do, but they can always be, at least in theory, converted into one another. And this is called the conservation of energy. It's really called the conservation of mass energy, though this is beyond the scope of this course. But Einstein's law of E equals mc squared tells us that energy equals mass times the speed of light squared. And while this tells you how much energy you get when you convert mass to energy, what it really tells you is that energy and mass are two different versions of the same stuff of the universe. So you're not responsible for understanding this interconversion between matter and energy, or mass and energy, but it's an important point to be made in general. But for now, you're just going to treat this as a conservation of energy. So you add up the forms of energy in the beginning, you add up all the forms in the end, and they should be the same total amount of energy. So energy can be transferred between what we call a system and what we call the surroundings. So the system is just whatever object or group of objects you're interested in at the moment, and everything else around it is called the surrounding. And when you're performing work, this is one of the major ways of transferring energy from one system to another, one object to another. Transferring heat is another way. Transferring matter with its own stored energy is a third way. You're not responsible for those, but you should understand what work does. And I'll scroll down a little bit. So here are a few examples where energy is being converted from one form to another as some action takes place. And the first one in this list is a moving hammer drives a nail into wood. Well, what's happening in the beginning? In the beginning, the hammer is moving. Movement of matter means there's kinetic energy. And that kinetic energy is used to create work on the nail. So the nail is hit and the nail is driven into the wood, causing the nail to move. That's new kinetic energy. And the wood to deform. That's a different form of energy. That's a form of non-mechanical energy. The second example, an object falling. So initially it's at a higher height, so it has gravitational potential energy. But as it falls, it's going to start moving faster and faster. So that gravitational potential energy gets lower and lower because it's going to a lower position, but it's also moving faster, so the kinetic energy increases. And eventually it will impact the ground and transfer heat to the ground, and heat is a form of transfer of energy. So the ground will become warm, and that means the ground now has thermal energy. And then in the process, there'll be some noise, and that is sound or acoustic energy. Third example, a lifted weight drops. Well, again, you have an object with height, so it's going to have gravitational potential energy. As it falls, it will gain kinetic energy, but lose gravitational potential energy. Eventually, it hits the floor. It's doing work on the floor by moving parts of the floor in a dent. That's a form of work. And then the floor itself gets deformed. And then the last example is a spring-loaded toy gun launches a Nerf dart. Well, a spring-loaded toy gun has a spring in it. So when you compress the spring, you actually do work to get the spring compressed. Once it's compressed, it has elastic potential energy. That's the energy of a compressed or extended spring. In this case, it's usually compressed spring. And then once that gun is fired, its energy is converted to kinetic energy as the spring starts moving, and that in turn launches the Nerf dart. Well, by moving another object, that's a form of work. And then the Nerf dart gains speed, so the Nerf dart gains kinetic energy. But in all of these processes, at any one moment, if you asked, what are all the forms of energy present at this moment and how much of each, the total will always be the same everywhere along the way, as long as you're counting everything. And when I say counting everything, if for some chance you picked a system and some of the energy went to the surroundings, you may not count it. But we're going to generally count all of the energy. And you're really just looking for all the various homes that the energy has. Is it in kinetic energy? Is it in gravitational potential energy? Is it in elastic potential energy? Is it being used to produce work on something? Is it going to some non-mechanical forms of energy, like internal energy or thermal energy or acoustic energy or deformation? So energy always has a home, but that home or that group of homes will change constantly when something is happening. And we have a variety of different methods that we use to diagram the energy as it's moving. We use pie charts, we use bar graphs, and we use something called an LOL, energy flow diagram, to represent the movement of energy from one form or location to another. And these are diagrams that are going to be used in the PHET Gate Park lab that you're going to be looking at. Now, it's already been mentioned several times that mechanical energy is merely the sum of kinetic energy and the various forms of potential energy. And that kinetic energy and potential energy are useful for performing work. They're very easily converted into work in order to move objects or produce change. So the mechanical energy equals the kinetic energy plus the sum of the various potential energies, but I never really went into any detail about what kinetic energy is or what the various potential energies are. I will tell you that we're going to go over each of these, and we're going to cover two forms of potential energy, the gravitational potential energy and the elastic potential energy. But for a falling object, it doesn't really involve any elastic potential energy. There are no springs involved when an object is just falling. What is involved is gravitational potential energy, because initially it starts off at a high position, and then as it falls, it will move, so it has kinetic energy. So the mechanical energy in a falling object is just the sum of those two energies. So let's look at what these energies actually are. And we're going to start with the kinetic energy component of mechanical energy. So kinetic energy is merely energy in an object due to the fact that the object has motion. It has some speed. The mass must have speed to have kinetic energy. In fact, to have kinetic energy, it has to have mass and it has to have speed. And the mass is going to be measured in kilograms. Speed is going to be measured in meters per second. And no speed means no kinetic energy. Simple as that. The formula is kinetic energy equals 1/2 times the mass times the speed squared. And we use speed instead of velocity because we really don't care which direction the object is moving, and we're going to square it anyway. So even if it was a negative sign, it would be squared, and the square would lose the negative sign. Everything would become positive. But the important point here is that the kinetic energy is directly proportional to mass. So if you double the mass, you'll double the kinetic energy. If you triple the mass, you'll triple the kinetic energy. But the kinetic energy is also proportional to the speed squared, not just the speed, but the speed squared. So whatever you do to the speed, you square that to find out what happens to the kinetic energy. So if I was to triple the speed of an object, the kinetic energy wouldn't increase by threefold, it would increase by 3 squared fold, and 3 squared is 9, so that would be a 9-fold increase. So for small changes in velocity, you get big changes in kinetic energy. As a result, the dependence on the speed of an object becomes very important for kinetic energy. Potential energy, the other part of mechanical energy, has various forms, as I've mentioned, but potential energy in general, I've never really given you a detailed explanation. This is the energy in an object, that's stored energy. You can't really see it. It's not necessarily a moving object. The stored energy is because the object happens to be in an unusual position or some unusual configuration that makes it relatively unstable. It does not want to be in that position, and if you were to let it go, it would start doing something. And there are many types of potential energy, and each one has their own calculation. The only one you're going to be responsible for calculating is gravitational potential energy. And oddly enough, you've actually done this calculation because it's nearly identical to when you're calculating work for vertical movement of an object. So let's talk about gravitational potential energy first. So gravitational potential energy is stored energy because the object is high above the ground level. It's not at its most stable position. Falling down to ground level would be its most stable position. So anything above ground level is considered somewhat unstable, and therefore that is energy added to the system. It's stored in the object because it's being pulled down by gravitational force, and it has some height above the ground, and because of that, the calculation for gravitational potential energy is very dependent on the height. It's also dependent on the mass and the gravity of whatever planet you're on. We're on Earth, so we're going to use G for the acceleration due to gravity. So the formula is merely m times g, which you know is the weight of the object, times the height. Well, this is the same formula for calculating the work to lift an object up. So once it's up there, it has a certain gravitational potential energy equal to m times g times h. And the mass will be in kilograms as always. G will be 9.8 meters per second squared. Occasionally we might round it to 10 meters per second squared. And h, the height, will be measured in meters. And as I said before, vertical work is the same formula, m times g times h, because it requires a certain amount of work to get the object up high, and once it's up high, it has that much energy stored in it in the form of gravitational potential energy. So those are exactly the same amounts. And remember, this is due to the fact that we have conservation of energy. I put a certain amount of work energy into the object to move it, and now it possesses a certain amount of gravitational potential energy because of its unusual high location. Now, there are other kinds of potential energy. Elastic potential energy is a form of energy that's stored in an elastic object, a springy object, some object that can be either compressed or stretched. So springs are a perfect example of that, but there are other materials that will behave something like a spring. Even rock in geological studies will behave a little bit like a spring when it's under great pressure. It will be compressed, and when it's stretched by other forces, that's also a form of elastic potential energy. But we're going to mostly talk about things like springs. So elastic potential energy is dependent on how much stretching or compression happens relative to the unstretched state. So if you had a spring that was totally relaxed in the middle, and I'll just draw it, so if I imagine a spring that looks like this, there is no elastic potential energy in this spring. But once I either compress it together or I extend it out and stretch it, now it's been stretched by a certain amount or it's been compressed by a certain amount. We'll call that amount X, that distance X. And the formula for elastic potential energy is 1/2 times a constant we call the spring constant. It's different for every material. You'd have to look up the K for that material, and then you multiply it by how much it's either compressed or how much it's stretched squared. But this formula is one you are not responsible for. So I'm just showing it to you, but we are not going to give it to you on an exam. You just need to know that the elastic potential energy is dependent on the stretching or compressing of some type of springy elastic material. So again, the mechanical energy is just the sum of the kinetic energy and the various potential energies. So it's the kinetic plus the gravitational plus the elastic potential energy. But for a falling object, we don't worry about the elastic potential energy. We just consider kinetic energy as it's falling and the gravitational potential energy dependent on how high the object is at that moment in time. So this is dependent on the speed at any moment in time, and this is dependent on its height at any moment in time. But if you measured it as an object falls, initially it will have only gravitational potential energy, and when it just before it hits, it'll only have kinetic energy because it's not any height above the ground. And in between, it'll be this mix of gravitational and kinetic energy as the gravitational potential energy is converted into kinetic energy while it's falling. So that's mechanical energy. Now let's look at non-mechanical energy. So non-mechanical energy is what is remaining from the total energy. Total energy is the sum of mechanical and non-mechanical energies. So anything left after we calculate mechanical is the non-mechanical. And the non-mechanical energy is not very useful for performing work. It possibly can be used, but it's very difficult. Now, non-mechanical energy is composed of a variety of different energies that involve position and movement on the atomic level, the molecular level, or even smaller than the atomic level. And you're responsible for just knowing the existence of 3 of these. You don't have to calculate them. You don't have to know any details about them. You should just know these 3 are the forms of non-mechanical energy. And what are they? Internal energy is essentially the movement of atoms and molecules at a very, very tiny scale. Sound energy is the movement of the molecules that carry sound through the air or through solids or through liquids. This is more accurately referred to as acoustic energy, but if you just said sound, that would be fine. And then the third one is deformation energy, also known as elastic strain energy. And please do not confuse elastic strain energy with elastic potential energy. Elastic strain energy is just deformation energy. That's a type of non-mechanical energy. Elastic potential energy is a type of potential energy, and that is part of the mechanical energy. I know these get confusing. Look at the tree diagram a couple pages back to clarify the organization of the different energies. And this is the energy involved in deforming the shape of an object especially after it's had some kind of impact. All right, so you really just need to know those three exist, and these are especially important when one object hits another object. It will transfer some of its microscopic motion and positions to the atoms that it's contacting. Technically, those are forms of kinetic energy and potential energy, but we do not count them as mechanical energy. That will often make a sound. We will hear it. That is because acoustic energy has moved through the molecules in the air before it's reached our ears. And then deformation energy, if when the impact happens, something got bent or broken or crushed in some way. So that's non-mechanical, and that's really all you need to know about non-mechanical, and that the total, as I said before, the total energy is going to be the sum of mechanical and non-mechanical, and those energies can shift, but the total will always remain the same. And if you have calculated the mechanical energy from the total of kinetic and potential energies, if you've already done that and you know that value, and you know the total energy, because maybe in the beginning of some interaction, all of the energy was mechanical, so you can get the initial energy that way, and that's the total energy. You just subtract out the mechanical at any one moment in time, and that will tell you the non-mechanical at that moment in time. So for a falling object, the non-mechanical is just the total energy minus the mechanical energy, and the mechanical energy is just going to be the sum of the kinetic and the gravitational potential energy, because that's the only potential energy that's really that important in the case of a falling object. And you could write it the way I have it here, or you could take the parentheses out and make both of these negative signed energies. So now you have the understanding about the different energy forms and the ability to calculate a few of them. Let's look at some energy calculation problems. Number one, if a 798 kilogram car is driving with a speed of 11.2 meters per second, that's about 25 miles per hour, what is its kinetic energy? Well, we have a very straightforward formula for kinetic energy. Kinetic energy equals 1/2 mass times the speed squared. Well, here's our mass. Anything with kilograms is our mass. Label that mass. And here's our speed. So we just plug these numbers in. 1/2 times 798 kilograms times 11.2 meters per second. And we have to square that quantity. So we're going to plug that into a calculator. And if you want to do the square first, this number squared is 125.44. If you were counting the units, you are squaring meters per second, which means that the meters are squared and the seconds are squared. Now you plug this in and you will get a final answer of 50,051. And if you look at the units, you've got kilograms, meters squared per second squared, kilograms, meters squared per second squared, but that's the same as a joule. So this is 50,051 joules of energy. Roughly 50,000 joules of energy. Now, looking at the second problem, we have the same car, 798 kilogram car, but now the speed has been increased to 16.1 meters per second, about 36 miles per hour, about 35, 36 miles per hour. And this is what we typically do when we're in a 25 mile per hour speed limit zone. We frequently will say, oh, it's going 10 miles per hour extra, 12 miles per hour is no big deal, and we'll go a little bit faster than the speed limit. But let's see what happens to the energy. The formula is still the same formula. The mass is still the same, 1/2 mass times speed squared. We plug this in, 1/2 798 kilograms, just like before, and we've got our 16.1 meters per second speed. We have to square that. And when we square 16.1 meters per second, this number jumps up to 259.21 meters squared per second squared from the squaring. Now we plug this into the formula, so we're multiplying these numbers together, and this time we get 103,425 joules, double what we got in the last problem. We only increased our speed from 11.2 meters per second to 16.1 meters per second. We went from about 25 miles an hour to about 35, 36 miles an hour. But we doubled the energy of the car. In fact, one of the reasons that speed limits in residential neighborhoods are set to 25 miles per hour is because about 2/3 of people, when hit by cars at that speed, will actually survive. But most people hit at 35 miles per hour will not survive. So a small change in speed results in a big increase in mortality from being impacted by an automobile. And this is because kinetic energy is highly dependent on the speed of an object. It is proportional to the speed squared. Small changes in speed result in big changes in kinetic energy. Number 3, a 55 kilogram student, so that's the mass, anytime you see kilograms, that's the mass, is about to dive from a 45-meter cliff. All right, well, let's do a quick drawing of that. We've got this cliff, we've got the person up at the top here, and the height of the cliff is 45 meters, and that person has a mass, 55 kilograms. And we know G is 9.8 meters per second squared. What is her gravitational potential energy? Well, the formula for gravitational potential energy is mass times the acceleration due to gravity. That's because that is the weight times the height. So we just plug those three numbers in. 55 kilograms, 9.8 meters per second squared, G, and our height is 45 meters. So the gravitational potential energy is very dependent on height. We plug these numbers into our calculator and we get 24,255 joules. So it's that much gravitational potential energy. Number 4, if a 5,000 kilogram boulder is sitting on ground level, what is its gravitational potential energy? Well, remember the formula, gravitational potential energy is mgh. But if h, ground level, that's 0 meters high. If we plug in 5,000 kilograms and 9.8 meters per second squared for g, it doesn't matter how big our boulder is. If it's sitting on ground level, there is no height above ground level, and therefore the gravitational potential energy is 0 joules. Now the last question in this set has 3 parts. Number 5 says a 63 kilogram cliff diver has leapt from a tall cliff into the ocean. At one point, the diver is 75 meters above the ocean and traveling at a speed of 23.6 meters per second. A, what is the diver's kinetic energy at this moment in time? B, what is the diver's gravitational potential energy at this moment in time? C, what is the diver's mechanical energy? Let's start with each formula. Kinetic energy equals 1/2 mass times speed squared. Gravitational potential energy equals mass times the acceleration due to gravity, g, times height. And mechanical energy is just the sum of these two. The kinetic energy plus the potential energy, but the only potential energy we care about is the gravitational potential energy. Solving the first one first. Remember, there's a cliff. The diver is going to jump from the cliff. Do we care about how tall the cliff is? No, because we care about a moment in time when the diver is already falling. They're somewhere here, and they are still 75 meters above the ocean, and they have a speed at this moment in time of 23.6 meters per second. You can use the speed and the mass to calculate kinetic energy, and you can use the height and mass to calculate gravitational potential energy. Let's plug these in. Kinetic energy, 1/2 times 63 kilograms times the speed squared, 23.6 meters per second, quantity squared. We plug this into a calculator and we get 35,088 joules. We now look at the gravitational potential energy. We got mass times g times height. 63 kilograms times g, 9.8 meters per second squared, times a height of 75 meters. Remember, at this moment in time, the diver is moving this fast and they are this high above the ocean. We plug those three numbers into the calculator, we multiply them, and we get a gravitational potential energy of 46,305 joules. And now for mechanical energy, we just add them together. 35,088 joules for kinetic and 46,305 joules for gravitational potential. We add them together and we get a total of 81,393 joules of mechanical energy. And there's a fourth part to this problem that says, how did the total energy change after the diver hit the water? Well, this question is really one that you have to read and think about carefully. Remember, the kinetic energy went to 0 joules because the diver stopped moving. And the gravitational potential energy also went to 0 joules because the diver got to ground level, or in this case, ocean level. So those both went to 0, but the total energy never changes as long as you count everything. Remember, total energy is conserved. It's just converted into other forms. So our mechanical energy, that's composed of gravitational potential energy and kinetic energy, is all turned into non-mechanical energy in this particular case. And that non-mechanical energy is composed of energies like internal energy of the water is now increased from the impact, and you might also have a sound, so there's acoustic energy. And if this was a solid that the diver landed on, there would be deformation energy as well. You could argue there might be a little deformation energy because of deformation of body parts of the diver when they hit the water, hopefully nothing permanent. So I'll put deformation in parentheses. That would be a third one that you would have in most other cases. It's just in water, we just don't typically call it deformation. So all of the energy that used to be mechanical energy is lost because the diver stopped moving, no kinetic energy, and landed at the bottom, 0 gravitational potential energy. But that energy has to go somewhere, and it went into a combination of different energies that make up the non-mechanical energy. But the fact is, the total energy never changed. There is conservation of energy. And this is a good place to stop.